Hello again. This is a Math Club work product coming to you from the College of DuPage. And the title of this video is Number Theory, Those Who Do Number Theory, A Shallow Dive. By way of introduction, recent Learning Commons discussions with Jesse Hayes Carver spawned an idea for some Math Club projects addressing mathematics beyond COD's scope. This is one such video note about number theory. We talk briefly about what it is and what some number theorists look like. And my main source on this, and this whole video was inspired by an article by Jordana Sepowitz, and she was writing for Quantum Magazine, and this is what another young scientist looks like. Our discussion begins, as many discussions do, in math history. And this is a picture over here of a scroll known as the Rhine Papyrus. And this dates back to 1650 BCE. And this talks about how ancient Egyptians represented rational numbers as sums of unit fractions. Unit fractions have a 1 in the numerator. And we know now, and perhaps they knew it also, although not this using these words, that any rational number between 0 and 1 possesses a Euclidean fraction decomposition, which writes x as the sum of fractions with unit numerators. And one constructive proof uses a greedy algorithm, which keeps subtracting off the unit fractions of the form 1 over, and this is the ceiling function of 1 over x. And certainly you can write computer code to implement this greedy algorithm, and here we do it for 21 over 23. And this says in the greedy algorithm that 21 over 23 is in fact the sum of these unit fractions. Now the denominator over here is really enormous, and so there are more efficient algorithms, and I invite you to perhaps think about those. But the modern day interest in such sums got a boost in the 1970s when a couple of people, Paul Erdős, and Paul Erdős is shown here, and Ronald Graham is shown here, came up with a conjecture. There's a little nice story, I suppose, that goes here. Ron Graham was the chief scientist at Bell Laboratories when I worked there, and Paul Erdős met Ron Graham at a math conference where there was a table tennis thing. And as you see here, Ron Graham was an incredible athlete. He could juggle 7 balls simultaneously with no sweat. But he met this fellow who was much older than him, and the older fellow, Erdős, challenged him to a table tennis match. And Erdős destroyed Ron Graham in this match. Ron Graham decided to really work on his game, and he became the Bell Labs champion at table tennis later. Here is also showing Paul Erdős meeting with young Australian math prodigy Terry Tao. And Terry Tao was really a child prodigy, but here you see Erdős working with him, and in fact, one of Erdős's conjecture, a very famous one, Terry Tao, who's now regarded as probably the #1 mathematician in the world, solved. So there's quite a lineage here. But anyway, going back to what we're talking about now, in the 70s, Erdős and Ron Graham asked how hard it might be to engineer a set of whole numbers that don't contain a subset whose reciprocals add to 1. You want to think about what that is saying. But as an example, this set fails the test because we can come up with a subset of this 2, 3, and 6, whose reciprocals are unit fractions, and if you add those up, you do get 1. So again, the question was, how hard is it to engineer a set of whole numbers that don't contain a subset whose reciprocals add to 1? More exactly, they conjectured that any set that samples some sufficiently large positive proportion of whole numbers, and the proportion could be 20%, 1%, or even 0.001%, must contain a subset whose reciprocals add to 1. If the initial set satisfies some simple conditions of sampling enough whole numbers, and they called this sample having positive density, then even if its members were deliberately chosen to make it difficult to find that subset, the subset would nevertheless exist. This again is an existence proof. Now, the hero of our story is a young man at Oxford named Bloom, and we'll say more about him later. But his involvement with Erdős and Graham's question, that was in the 70s, recently grew out of a homework assignment. Last September, he was asked to present a 20-year-old paper to a reading group at Oxford. That paper was by a mathematician at Georgia Tech named Ernie Krut, who solved the so-called coloring version of the Erdős-Graham problem, a reduced version of this. There, the whole numbers are sorted in random into different buckets designated by color. Some go in the blue bucket, others go in the red one, and so on. Erdős and Graham predicted that no matter how many different buckets get used in this sorting, at least one bucket has to contain a subset of whole numbers whose reciprocals sum to 1. Now, Groot introduced some very powerful new methods from harmonic analysis, a branch of math closely related to calculus, to confirm the Erdős-Graham prediction. And his paper was a great one, and it was published in the Annals of Mathematics, which is the top journal in the field. And this was the paper that Bloom was to present at the reading group at Oxford recently. Yet, as impressive as his paper was, it did not answer the full density version of the Erdős-Graham conjecture. This was due to a convenience that he took advantage of what's available in the bucking sorting formulation and not the density one. And he showed that at least one bucket always satisfied the property, and so he did prove the coloring result. But the more general density version, where mathematicians cannot simply choose whatever bucket happens to be most convenient, they might have to look for a solution in a bucket that contains no numbers with small prime factors, and his method did not work for that. And here's a picture of Bloom, our current hero, the current subject of our discussion. So instead of using Krut's method to hunt for sets whose numbers reciprocals add to 1, he employed similar techniques to find sets whose reciprocals add up to smaller constituent fractions. He then used these as building blocks to get the desired result. Here's a quote from him. "You're not finding 1 honestly. You're finding maybe 1/3, but if you do that 3 times in 3 different ways, then you just add them together and you've got that." Actually, this is an honest approach. He's being a little bit glib with that comment. But this left him with a much stronger statement, much stronger than Krut's, about how robust this numerical pattern is. So long as the set contains some tiny but sufficiently large sliver of the number line, and that's the proportion that Graham and Erdős were talking about, no matter what the sliver looks like, it's impossible to avoid finding these neat sums of unit fractions. And as good mathematics almost always does, at the same time, it leaves mathematicians with a new problem to solve, this time about sets in which it's not possible to find a sum of unit fractions that equals 1. The primes are one example. There's no subset of primes whose reciprocals sum to 1. But this property can also hold true for other infinite sets that are larger than the one we just talked about, in the sense that the sum of their reciprocals approaches infinity even more quickly than the reciprocals of the primes do. Just how quickly can those sums grow before hidden structure reemerges and some of the reciprocals inevitably add to 1? And this, of course, is a research problem, but this statement, there's no subset of primes whose reciprocals sum to 1, proving that statement, that there's no subset of primes whose reciprocals sum to 1, should be well within your reach. I encourage you to give it a go. In closing, time is precious. Each day must count. Do the math. It will make you strong. And, as always, take care of yourself and of each other. God bless you all.